Alright, so example 3 from 5.3, we've got a triangle here, nothing special about it. Looks like an acute triangle based on each angle being less than 90. I'm going to use a little measurement tool here, and my ruler's not going to scale the same as your ruler, so the numbers I get won't be exactly the same as you, but you guys have a ruler in your possession. What I want you to do is I want you to measure each side of this triangle, and you be as precise as possible. So if I take my ruler here and I place the 0 on A, be careful that 0 is not at the very edge of the ruler, it's like a little bit in there. And then you open up to B. Again, be as precise as possible that you're sitting right on A, 0. And I'm getting a measurement of about 9.95 maybe. Almost makes it up to 10, but not quite. So half of 9.95 would be right around 5, right? So I'm going to put try and get like right between 4.9 and 5. So like right about there. Okay. So that right there would represent the midpoint of AB. Again, using measurement tools, we could obviously perform construction to find the bisector of AB. We could find the exact point, but just to save a little time today, we're going to use rulers to measure. So that's 4.95, about halfway between. Oops. Then I'm going to move my ruler down here, do the same thing for AC, make sure I'm right at 0 on A. Looks like it goes to about 10.4 on my ruler. So half of that would be 5.2. So right about there. Oops. And then finally, if I bring my ruler up to either B or C and measure from B to C, it's right at 0 there, and measure, comes right at 12.5. Half of that would be 6.25. Right about there. And I use the arrows instead of a dot because my ruler, if I touch anywhere near the ruler, wants to draw a line, so I do the arrows there. But so if I put a dot at each of these locations, so a dot here, a point here, that's the midpoint, and we're going to call that, let's see, let F be the midpoint of AC. They want this to be point F. Let D be the midpoint of AB, so this is D. Let E be the midpoint of BC, that'd be this point right here. Just have to leave that red one there. So, if I connect those midpoints to the vertices, those are medians, as we talked about on Friday, right? So a median is a segment drawn from a vertex to a midpoint in a triangle. So if I were to connect each of those, they should intersect in one point on that triangle. Again, there's experimental human error to this, so we might be off by just a smidge, but they should be pretty close. So if I go from D down to C, so this midpoint of that vertex, again, be as precise as possible when you draw this. And then go from B down to F, and then go from A over to E. And you see there, they do pretty closely intersect at that spot, right? So this point of intersection of the three medians is to be named point G. and you put the G wherever it fits. Just a little experimentation here, we can create this. Now, if you were to do this with a piece of cardboard, you can see here I've got this triangle here that I did earlier, and I've got my midpoints. I just drew enough so I can find the centroid, the center of gravity. And you place an object, a sharp-pointed object, on that center of gravity, like so. You can see that it's not quite perfect, but you can see it tried to balance. That's what we're finding here is the actual center of gravity. Try one more time. Got to be right on top of that point. There you go. Oh, I missed by a little bit. So again, that's human error to that, but you can see it tried to balance a little bit. I was really close to it. I wasn't dead on it, but if I was, it would have balanced right there on that pen. So the other property we learned on Friday about center of gravity, that centroid, that point G where the medians intersect, is that the distance from a vertex along the median is 2/3 to this point and 1/3 to that point. So I'm asking you to measure the length of AE, AG, and GF. Again, my ruler is not the same AE, AG, and I should say GE. This should say GE here. AE, AG, and GE. Okay, so the measurements I get won't be the same as yours, but I'm just going to use my ruler to take measurements here. We can take a look, and you can do it on your own paper also. But if I place my ruler at 0 at A and I open up to E like so, it looks like, you know what, I can actually change the ruler a little bit. I'm trying to get a number divided by 3 nicely, so let's see what I can do here. That's pretty close. There we go. I got mine set 8.1 centimeters all the way from A to E. And again, your ruler obviously might not have the same numbers mine do because of the scale, but if AE is 8.1 centimeters, and AG is 5.4 centimeters, and GE is 2.7 centimeters. That's the measurements I get. But again, the fact that my ruler is a different scale than your rule doesn't change the fact there's going to be this 2/3, 1/3 relationship. So it says AG is 2/3 AE. So AG 5.4 is supposed to be 2/3 of AE, which is 8.1. Question mark. All right, to multiply by 2/3, we first divide by 3, then multiply by 2. 8.1 divided by 3 is 2.7. 2.7 times 2 is 5.4. The other way, of course, is just if you use a calculator, if you type in 8.1 times 2 divided by 3, that's times 2/3. It also spits out 5.4, as you can see. So that verifies that AG is 2/3 of AE. And then, of course, the other part, GE, which is 2.7, should be 1/3 of AE. So 2.7 equals 1/3. 1/3 times 8.1. 8.1 divided by 3 is 2.7 times 1 is 2.7. Again, there's a question mark up here. There's not one right there. So that just verifies that theorem in one specific setting. That's not a proof. Proof is not showing it works once. Proof is showing it works every time. But again, that's just a quick little way to verify at least that it is possible for this to happen.